Hello everyone, welcome to the video explanation for Brian Passwater's topic 2-3 notes over exponential functions. We're going to start with a video of the key characteristics, the essential knowledge for exponential functions. In general form, an exponential function will always be in the format f of x equals a times b to the x power, where b is greater than 0, a and b are constants, and a is not equal to 0, b is not equal to 1. So let's talk about that a little bit. In that situation, the a is going to be our initial amount, or on the graph, that will be our y-intercept. The b value will represent the common ratio, but in reality, we're going to probably more accurately describe it as the base of the exponential. That's the word we used in our algebra classes. And this is not a sequence, so calling it the common ratio it's connecting it to sequences, but it may not be the best way for us to phrase that. Now, when we look at this, again, it is essential that a is not equal to 0 and b is not equal to 1. The reason for this is, if a is equal to 0, the entire function instantly becomes equal to 0, which makes the function not exponential, but rather a constant function. Same if b is equal to 1. If b is equal to 1, then whatever exponent we raise that to, it would still equal 1. And then the whole function would equal the value of a, making it a constant function, not an exponential function. So those restrictions are in place. The other thing to notice is that b has to be greater than 0. Remember, that means b is a positive number. It cannot be negative, and it cannot equal 0. It must be greater than 0. Now, in the real world, we see two types of exponential functions, exponential growth and exponential decay. Those are shown in the graphics there. Exponential growth occurs when a is greater than 0 and b is greater than 1. And exponential decay is when a is still greater than 0, a is positive, and b is between 0 and 1. So in real world situations, again, we're looking at this a is greater than 0. Well, that means that a is positive. And again, the base is greater than 1. Same thing over here. A is greater than 0 means a is positive. So we need to keep that in mind, that real world situations, we're going to have a positive a value. Okay, the b's, if b is greater than 1, the function will grow. And if b is between 0 and 1, the function will decrease, meaning it will be decay. In terms of increasing and decreasing, there are some very important things to understand about exponential functions. Exponential functions are always increasing or always decreasing. They never, ever switch from one to the other, which means they do not have relative extremes. There are no local maxes or local mins, because the function never switches from increasing to decreasing, and it never switches from decreasing to increasing. Same thing for concave up and concave down. Every exponential function is either always concave up or it is always concave down. As a result, there are no switches in concavity, which means there are no inflection points. Now, in terms of end behavior, when we look at end behavior for this function, just like we do any function, we're talking about when the input, the x's, increase without bound, which is the right end, or decrease without bound, which is the left end. When we do that, one end of the function will either increase or decrease without bound, will go to positive or negative infinity, and the other end will always approach 0. A horizontal asymptote. So when we look at an exponential equation, an exponential function, and we have our end behavior limit statements, there are only 3 values that the end behavior of an exponential function will ever have. They will either go to positive and negative infinity or 0. And we can also know one end will go to either infinity or negative infinity, and the other end will go to 0. Now, the reason behind this, and this is not in Brian's notes, this is something that I write out for my kids, is that there are really only 4 types of exponential functions. We have exponential growth and exponential decay, which we've already talked about. Okay, exponential growth is where a is greater than 0, b is greater than 1. On an exponential growth equation, the entire equation is concave, the entire graph is concave up, and the function is always increasing. For exponential decay, again, that is where a is positive and b is between 0 and 1. The graph is always concave up still, but it is also always decreasing. Now, there is a possibility that we could be dealing with math problems that are not super real world, in which case we could have a negative a value, because the only restriction on a was that it can't equal 0. So if a is a negative value, we know from Unit 1 that that means it has been reflected across the x-axis. So there are two situations where that could happen. We could have vertically flipped growth, which is where a is less than 0 and b is greater than 1. In that situation, the graph is always concave down and the graph is always decreasing. Or we could have vertically flipped decay. In that situation, again, a is negative, that caused the vertical flip, and it's between 0 and 1. That graph is always concave down and will always be increasing.